We've already looked at some techniques for solving quadratic equations. Specifically, we were using a lot of factoring to solve quadratic equations. But what we'd like to do now is take some of these techniques we were using on quadratic equations and actually use these same techniques to solve equations that aren't quadratics, but they have properties that are very similar to the quadratic equation. So let's just remind ourselves, a quadratic equation is something of this form, right? Ax squared plus bx plus c. And if we have the quadratic equation, we have a few ways to solve this. Maybe we could factor, maybe we can complete the square. We can always use the quadratic formula if we have to. But what we're going to look at now is a way to solve some other equations using some basic ideas from solving these quadratic equations. So we're going to look at some equations that are almost quadratic, or what I like to call quadratics in disguise. So let's take an example, something like this. Okay, x to the fourth minus 13x squared plus 36 is equal to 0. Definitely not quadratic because we have an x to the fourth hanging out. So we can automatically throw that out. But what I like to say here is that this is almost a quadratic equation. In fact, I think we could write this equation so that we have something squared minus 13 times something to the first power plus 36. Because this is a quadratic form, right? Something squared plus b times something to the first plus c. And actually we can do this by, instead of writing x to the fourth, maybe I can just rewrite this as x squared squared, which if you know our exponent rules, these are equivalent, right? Because we would normally just multiply the 2 and 2 together to get the x to the fourth. And then I can just leave this one as x squared to the first power, and that will give me back to the negative 13x squared that I have in the original. So really what I'm saying is this statement and this statement are congruent statements. They're the same. And I've just done a little bit of tweaking to them to make them look a little bit different. So now you can see that this is almost in a quadratic form. I'm going to do one more step to make this a little easier to look at. So instead of this x squared, I'm going to replace this with just a different variable. I'm going to replace this with the variable u. We'll call this u substitution. So I'm going to let u equal to my x squared. So now in this equation, instead of writing the x squared at every step, I'm going to write a u instead. So it's here, instead of x squared squared, I'll write this as u squared minus 13 times u instead of x squared, and then plus 36, and all that's equal to 0. Now this equation should look a lot more familiar to you because this looks like the quadratic equations that we've been solving already in this lecture. And in fact, I can factor this relatively easily. This will factor into u minus 9 times u minus 4 is equal to 0. So I'll end up getting two solutions here, that u is equal to 9 and u is equal to positive 4. Now here's the trick. We're not solving this equation for u because the original equation is in terms of x. I want to know what are all the x values that will work in this equation. So at this point I need to go back and do a resubstitution because u is equal to x squared. So now I can resubstitute u here, I can replace it with x squared. And so I have x squared is equal to 9, x squared is equal to 4. So that means that if I think about which x values should I be able to square to get 9, well, those x values will be 3 and negative 3. And then which x values can I square to get 4? Those will be 2 and negative 2. So for this equation, I'll actually end up getting 4 solutions that all should work in this equation. But again, the idea is that we took something that's not a quadratic, we wrote it in a quadratic form, and then used our u substitution to help us solve the equation. Let's try a different one. Because there's a few different forms that these can come in, and some of them are not so obvious. For example, in this equation, x minus 5 times the square root of x plus 6 is equal to 0. Now I claim that this is actually a quadratic form, or a quadratic in disguise. Well, how is it? Well, I have to think about what should I square here, and then what should I take to the first power here in order to keep these equivalent statements, in order to keep these equal to each other. Well, actually, if I want to get from something squared to x, I could always just square the square root of x, right? Or x to the 1/2 if you want to write it like that. And then here I can have, again, the square root of x to the first power, and I'll still have what I had in my original equation. So these are equivalent, so we're in good shape so far. We haven't done anything destructive to our equation. Now the next step is to do a u substitution to make this actually look like a quadratic equation. So we'll let u equal to whatever this expression is. In this case, it's the square root of x. And now I'll go through and replace the square root of x with a u everywhere in this equation. So this will be, instead of square root of x squared, it'll be u squared minus 5 times u plus 6, and all that's equal to 0. Again, this will factor nicely. So this will factor into u minus 2 times u minus 3. Since negative 2 times negative 3 is 6, negative 2 plus negative 3 is negative 5. So I end up getting two answers. U is equal to 2, or u is equal to 3. But again, I'm not solving for u, I'm solving for x, so I have to do a resubstitution here. And say, well, u is really equal to the square root of x, so I'll just go back and replace that here. Now to solve for x, all I need to do is square both sides of this equation. And I'll end up getting 4 and 9. So the square root of 4 is equal to 2, and the square root of 9 is equal to 3. So my solutions here, after I square both sides, I'll get x equals 4 and x equals 9. Let's try one more. How about this form? 2x to the 2/3 power plus 5x to the 1/3 power minus 3 is equal to 0. This might not be one that you would see and automatically think that it's a quadratic in disguise or a quadratic form, but in fact it actually is. Because I could take something here and square it and get back to x to the 2/3. I could take x to the 1/3 and square it, and I'll get back to x to the 2/3. Because remember, the exponent rules just say multiply 2 times 1/3, so that's 2/3. And x to the 1/3, if you remember, that's just the the cubed root of x. So that's how we'll interpret this at the end of the problem. We'll have to remember what that is. And here I can put, again, x to the 1/3. The key here is to make sure that both of these are the exact same variable. So that when you do your u substitution, you can just plug in the u's exactly there. So now, if I do my u substitution, I'm going to let u equal to whatever this guy is in the parentheses, so x to the 1/3 power. And so I'm going to put this equation, 2u squared plus 5u minus 3 is equal to 0. This will factor, but this is a type 2 trinomial, so I'll have to do 2 times 3, 2 times negative 3 is equal to negative 6. And then the two numbers that multiply to get negative 6 but add to equal 5. These are going to be positive 6 and negative 1. So again, this is hopefully something you remember how to do from the previous lecture with factoring, so I'm going through it relatively quickly. Then the idea is we factor this by grouping, right? So I can pull out a 2u here, and I'll get u plus 3, and then I can pull out a negative 1 here, and that will give me a u plus 3 here. Now I can factor this by grouping. This becomes 2u minus 1 times u plus 3 is equal to 0. So I'll get my two answers, u equals 1/2 when I set that equal to 0, and then u equals negative 3 when I set that equal to 0. But remember, we're not solving for u, we're solving for x here. So I actually need to do a resubstitution. So instead of u equaling 1/2, I'll think of this as x to the 1/3 equaling 1/2. And instead of u equaling negative 3, I'll think of this as x to the 1/3 is equal to negative 3. Now to solve for x, I can just get rid of this 1/3 by cubing both sides because the 3's will cancel out, and I'll end up with the x to the first. So then if I cube this side as well, 1/2 cubed is 1/8. And then the same thing over here. I can cube this, or if you want to think about it, x to the 1/3 is really the cubed root of x. So when you cube a cubed root, it cancels out. And then over here I'll get that -3 cubed is -27. So these will be the two answers that I'll get for this particular problem.